a place that holds a special place in my heart. As in the first 2 years of graduate school, I came here to learn the chops of being an astronomer. So this is me back in 2018 with my other astronomy buddies, where we got to play around, learn how to operate the telescopes on the mountain, drive them, stare at Jupiter, not drive them into the ground. But we had a great time, and I'm happy to be back here. Now, you may not know this, but astronomers, we're really detectives. Our goal is to piece together 14 billion years of cosmic time. Our instruments of choice are telescopes, both on the ground and in space. And the clues that we use to unravel cosmic mysteries consist of light across the entire electromagnetic spectrum, from gamma rays to radio waves. Though this is great, but it's a challenge to be a detective as an astronomer. When we look at the universe, we see objects nearby. This is an example of a spiral galaxy. Our goal is to understand how these things form with just images, pieces of light. Luckily, there's a special feature of light. It moves at a finite speed, 186,000 miles per second, 300,000 kilometers per second. That's huge. That's a huge speed. None of us can move that fast. But space is even more vast. And because of this, when we look out and we try to figure out how did this thing form, we can see things that are further and further away. And the further away we look, the older the light that we capture. So this is showing a spiral galaxy as imaged by the Hubble Space Telescope. 550 million light years away, older than when the dinosaurs roamed the Earth. And as we go further and further away, we can see kind of like what the adult stage of spiral galaxies look like, piecing together this picture, this mystery of cosmic evolution. This middle row, teenage years of spiral galaxies. A lot of changes going on. And the bottom row, infancy, hardly recognizable. So though we can't understand and rewind time to see how this spiral galaxy formed, we can piece together images at different distances, different epochs, times in the universe. We can also do this not just for individual galaxies, but huge collections of galaxies. And this is what I'm really into. This is an image taken by the Rubin Observatory. By a raise of hands, who's heard of the Rubin Observatory? All right, okay. Look up the Rubin Observatory tonight. This is an amazing telescope. The largest digital camera that humanity has ever produced is on this telescope. And we're going to map the entire sky, getting exquisite images, fainter objects than we've ever seen before. And this is an example of the first light image that was released a couple weeks ago of the Virgo galaxy cluster. This is the closest cluster to the Earth. And this represents the largest collection, gravitationally bound collections of galaxies in the universe. Hundreds to thousands of galaxies are clustered together in galaxy clusters. They're also remarkable because they're home to some of the most massive galaxies that have ever formed, these giant ellipticals, as shown here. And they all have this yellowish tint, indicating that they've lost their ability to form stars. We call these red and dead galaxies. They grew massive and they died. And you can also see these other fainter yellowish blobs. These are also elliptical galaxies as well, making clusters these cosmic graveyards. So this is Virgo. We also have an image here from Hubble of the Coma cluster. This is one of the most massive galaxy clusters in the universe. Also home to two gigantic elliptical galaxies among the most massive galaxies in the universe. And clusters are fascinating because they hold clues to the universe's biggest mysteries. the nature of this mysterious matter that we call dark matter, the expansion of the universe, how fast it's expanding. We can test this with galaxy clusters. So one reason is because galaxy clusters are so massive. Einstein predicted in his general theory of relativity that matter distorts the geometry of space-time. So clusters are so massive, they can warp space itself, and light from distant objects can be bent and warped and modified in all kinds of ways. You can even get multiple images of the same galaxy. These clusters act as what we call gravitational lenses, in the same way the lenses that you can play around with, just don't kind of put it at the sun and in your eyes. Clusters do the same thing. They can modify and bend light. And we can learn so much from the universe by studying these clusters. This is another beautiful image from the James Webb Space Telescope. This is Planck G165.7. Beautiful name, right? We call these telephone names. It's located about 3.6 billion light years from Earth. So this light is ancient. And it's doing all these crazy things to the light around these distant galaxies, warping them, bending them. And I want to draw your attention to this spot. So these kind of arcs are distant galaxies that have been multiply imaged and warped. And if you look closer, there's these 3 dots. 1, 2, 3. Anyone want to guess what these are? You can just shout out the answers. Little galaxies, okay. Any other guess? Same galaxy. Black holes. I feel a lot of awesome answers. So these 3 dots are part of this kind of red galaxy that's been stretched out. They represent a star in its death throes. We call these a supernova. There you go. So we were able to catch a star going boom. When the astronomers that got these images from James Webb, they looked at it and said, wow, what is this? There's a special type of supernova. It's a supernova where we can infer its maximum brightness as it happens in a very special way. So this is the name of it. We call it supernova hope. And this is a visualization of what we think happens. You have a red giant star in this white dwarf, this hot, dense remnant of a sunlight star, siphoning off gas from its neighbor until it reaches a critical limit and explodes. And this is supernova. So we know the physics of what drives this. We can infer the brightness that this should occur, and we can measure brightness. From this, we can infer distances. And because it's been multiply imaged, this light is split, and it's taking different paths to reach us here on Earth. Space is expanding. We can use all this information to backtrack the expansion rate of the universe. Another amazing reason that we study galaxy clusters, unlocking the mysteries of the universe. In addition to being extremely massive and warping space and time itself, galaxy clusters are extremely, extremely hot. Now, you wouldn't notice this by looking at this image of the Coma cluster in the optical, the light that our eyes can perceive. But if you're able to put on your X-ray goggles, and we can do that with our tools, we are detectives. We have observatories that can see an X-ray. This is Chandra X-ray Observatory. If you stare at this cluster, you see that it glows. It glows in X-ray. This is due to the presence of a superheated gas. The gas is so hot that the electrons and the atoms are stripped away, creating what we call a plasma. And this gas in clusters, we call it the intercluster medium. Now, I want to give you some cool cluster facts so you can go home and tell your friends what you learned tonight about the intercluster medium. So the intercluster medium is between 1,000 to 10,000 times hotter than the surface of the sun. This gas that's permeating galaxy clusters. It also outweighs the galaxies by a factor of 4. So most of the visible luminous matter in galaxy clusters is in the form of the intercluster medium, this hot gas. But it doesn't make up all the matter. The rest is in this form of matter that we don't know what it is, but we can detect as gravitational input. And this is another way that galaxy clusters can help us unlock the mysteries of the universe. We don't know what dark matter is, but by studying clusters, we can understand its properties and kind of rule out what it might not be. Here's an example. This is the Bullet cluster, located at 3.7 billion light years from the Earth. And there's two clusters here. You have the smaller cluster and the larger cluster. Some time ago, the smaller cluster smashed through the larger cluster, having this head-on collision. And you can't see it again in the optical, but again, we're detectives. We have tools, telescopes, sensitive to different portions of the electromagnetic spectrum. So here in pink, we're seeing the X-ray gas from the intercluster medium. And I've outlined kind of this shock wave. This is a bow wave, similar to when a boat moves through water. As this cluster moves through the hot gas, it drags it along. But using gravitational lensing, that I mentioned earlier, we can find out where most of the matter is. And we see that the gas gets dragged along, some of it gets left behind, but the matter itself acts as if a collision never happened. This tells us about the nature of dark matter. It's likely collisionist, weakly interacting. So another really cool thing about galaxy clusters that we can learn is its impact on the formation and evolution of galaxies. This is my expertise. Galaxy clusters have this intercluster medium that's so hot that when a galaxy moves through it, plows through this gas, the gas from the outskirts can be ripped away. So this is an animation showing this, and we call this process ram pressure stripping. And these galaxies are called jellyfish galaxies. We're really cute in astronomy. So this is a visualization, but this is an actual image of a galaxy in a cluster. You can see its gas getting shipped away. And this is one of the processes that we think drives this transformation from spiral galaxies to kind of these yellowish blobs that I showed you before in galaxy clusters. But another major mystery is the clusters themselves. How do these cosmic behemoths, largest gravitationally bound structures in the universe, form and grow? And that's something I'm currently researching. We want to answer this question because there's many other mysteries we can solve, such as the growth of the most massive galaxies. I talked about these giant ellipticals earlier. These are the most massive galaxies that the universe has produced. But how do they form? Today, they're like fossilized remains. But by studying clusters and formation, we can figure out how they grew, how they came to be. Was it through all these multiple mergers? Maybe extreme bursts of star formation. Those are two ways that we think galaxies grow. By studying the earliest formation of galaxy clusters, we can understand the impact of environment on galaxy evolution. I showed you these jellyfish galaxies. The question is, when does environment begin to strip away gas and suppress star formation? We can also understand the large-scale structure of our entire universe. So galaxy clusters represent the densest regions in the universe. There's less dense regions, and there's regions connected by these large filaments. We call this the cosmic web. By studying galaxy clusters, we can understand how they formed. And lastly, we can understand the formation of the intracluster, meaning where did this hot gas come from? When did it appear in galaxy clusters? Sorry. This is why we want to understand how these systems formed. Okay, now going back to the example I showed at the beginning, we have a spiral galaxy, and we can look at it at different distances, see how it looked in the past. We can do the same thing for galaxy clusters. So this is the Perseus cluster. It's another relatively nearby cluster located 240 million light years from Earth. But we can also look at clusters at larger and larger distances. So we have Abel 68, 2 billion light years away, Max 0416, 4.3, going along to all the way up to 11 billion light years away. This is the most distant galaxy cluster that we ever found. Something interesting, if you look at these first four, I've highlighted them in red. You can still see this population, these fuzzy blobs, these elliptical galaxies, these things that have shut down star formation. This tells us that these things formed a long time ago. 7 billion years ago is about halfway to the current age of the universe. But as we go even further away, if we finding galaxy clusters, 9 to 10 billion years ago, there's a dearth, there's a lack of these elliptical galaxies. In fact, we find a bunch of galaxies that are forming stars at a high rate, something like 10 to 100 suns per year. And this is fascinating because this tells us how these structures grow. In the past, they were these regions of extreme formation of stars. Today, cosmic graveyards. But how did that happen? So this is a kind of cartoon that I put together to illustrate this process. So here, all this is the cosmic web that I told you about. Clusters kind of lie at these nodes, and then you have these bubbles of emptiness that we call voids. So a cluster today looks something like this. You have this compact core of galaxies. A lot of them are red and elliptical, this red and dead population. But as I showed you in some of these images, as you go further back in time, one thing that we notice, these clusters are more extended. You have more blue galaxies, more star-forming galaxies. That's what these blue dots represent. As you go further back, we see these structures are extended and just full of star-forming galaxies. And this is the young cluster. Go even further back, this is what we think, theoretically, protoclusters, as we call them, should look. Extremely extended, and should be composed of a very dense core of galaxies that are forming stars at an enormous rate. But there's a challenge to actually observing galaxy protoclusters. The first one you may have been able to guess, protoclusters are enormous. So compared to the moon, which spans about half a degree on the sky, protoclusters take up about roughly a third of the full moon. Clusters themselves are actually rare, so we have to scan large swaths of the sky to even find these things. Additionally, the techniques that we've developed to find kind of these mature young clusters break down the further back in time that we go. As an example, this is the Coma cluster, which I showed you before. We can look at it at different wavelengths, the visible or optical, and X-ray and submillimeter. Clusters, again, are regions where galaxies are all densely packed together. But another way to determine this cluster is also looking for these yellowish blobs. That's one way that we can verify that this density of galaxies is a cluster. And also in the X-ray, as I showed before, by the presence of this hot plasma, the intercluster medium, it's also visible at longer wavelengths in the submillimeter. But as you go further and further back, these things break down. I showed you before that protoclusters lack this distinctive population of red elliptical galaxies. You go further back, most galaxies are star-forming. And the proto-intercluster medium should be cooler and less dense, making X-ray and submillimeter signals challenging to detect. So how do we make progress? So all we really have is to identify protoclusters by locating the densest galactic environments in the early universe. But this requires something that is very important in astronomy. The only reason that we know that there are other galaxies out there, measuring distances. And we need accurate distance measurements, again, over these wide areas of the sky. Now to illustrate why this is important, I have a little game here called Can You Spot the Imposter? So there's something called projection effects. We look at the sky, it's kind of 2D, but it's really 3D, right? And the things that can seem to be clustered together, but really aren't, just separated. So this is an example of Stefan's quintet. It's a galaxy group, it's not a cluster. It's also a dense environment, the most common dense environment, but not the most extreme. Now I've highlighted 5 of the galaxies here. So I want to, by a raise of hands, so I'm going to go through A, all the way through A to E, to see which of you can find out which is the imposter. All right, so starting with A, raise your hand if you think NGC 7320 is the imposter in this system. All right, we got 4 hands. B, got 1 hand. What about C? 2, okay. D, 4, okay, we're tied with A and D. And what about E? That gets everyone else, right? So it's kind of hard to see in this JWST image. If you look at Hubble, it might be a little easier. So the imposter here is NGC 7320. It's a galaxy that's actually located closer to us than the actual other 4 galaxies. So this points out the importance of getting these distance measurements. We can have these misaligned element of galaxies that make us think that we're actually seeing a concentration of galaxies is not actually there. But there's also an issue. Obtaining accurate distance measurements over vast areas of the sky is observationally expensive. So we have something known as a telescope allocation committee. You submit a proposal and you say, hey, I want to go look at this thing and measure it and do all this fun science. But if you just say, hey, I want to look at all galaxies and measure their distances, they will laugh you out the room. You would have to have a dedicated survey to do that. So one solution is to limit protocluster searches to galaxies that are unique to the distant universe. So one of the ways that we do that is using population galaxy known as Lyman and Break galaxies. Fancy name, but really just means a galaxy that's forming stars, something like 1 to 100 stars like our sun per year. It's just really far away. It's in the early universe. So showing in this illustration, you have the kind of distant galaxy, and all this blue stuff, this is gas. This is neutral hydrogen, a proton, and an electron. These streaks are the light from the galaxy. So what's cool about these galaxies is that if you look at their spectral energy distribution, so this is the amount of light comes from the galaxy as a function of their wavelengths. So here, the bluer colors, bluer wavelengths used are the redder. Because of this intervening gas, some of the light gets absorbed, and it leads to this characteristic, what we call Lyman break, the Lyman limit. So you can see this reduction of light that we observe just due to light being absorbed. Now, measuring this spectrum is expensive. You have to do something known as spectroscopy, but it's really cheap to take an image of the sky. So one way that we find these galaxies without having to actually measure all these bumps and wiggles is to take an image in different parts of the electromagnetic spectrum. So here is an image of a galaxy kind of in the redder filters. You can go bluer and bluer, and eventually the galaxy just disappears. So these are Lyman break galaxies, also known as dropout galaxies, because of this reason. So instead of asking for distance measurements and trying to get this spectrum, we can go into take all these images and just find the galaxies that do this, and then limit our searches from there. Because this gives us, lets us know that these things are likely distant galaxies. So this is actually how one of the earliest galaxy protoclusters were ever discovered. This is a serendipitous discovery of 16 Lyman break galaxies that were clustered together 11.5 billion years ago. This is kind of a plot showing the number of galaxies as a function of kind of time. These are things that are closer to us, further away. But I just really want to draw your eye to this huge pileup of galaxies. So this is the protocluster. And visually, it looks something like this on the sky. And this is a 3D representation. So these things don't look like the clusters we see today. They're more amorphous, many overdensities. So now we've come to a point where we've created what I dubbed the protocluster zoo. So these Lyman break galaxies are kind of these normal star-forming galaxies, 1 to 10, 1 to 100 stars like our sun being formed a year. And that's one way that we've detected protoclusters. People have been clever and come up with other ways as well. Another way is using a population of galaxies that are really, really dusty, so we can't see them in the visible or UV. But if you go to longer wavelengths, you can see them. And these things are forming stars at a really high rate, possibly representing this core, this theoretical core of the protocluster. And galaxy protoclusters have been selected that way. And this new method that's really exciting to me is looking for a population of galaxies known as ultramassive galaxies. These are galaxies that are 100 billion, masses that are 100 billion times that of the sun, but they're really early. So understanding how these things built up their mass so early is still an open question. But we think that they are in these overdense regions representative of galaxy protoclusters. And another really awesome way is looking for things known as quasars. So someone mentioned black holes before. There's something known as a supermassive black hole at the center of our galaxy, but it's not really doing much. Some supermassive black holes take in gas and dust, heat it up, and produce these jets of radiation. And people believe that if you can find these in distant universe, these could be tracers of overdense regions. So this is kind of a visual representation of our protocluster zoo. These are what protoclusters look like, these high redshift or this distant concentration of galaxies. Now, if you look at the cumulative number of discoveries of galaxy protoclusters across time, it looks something like this. So since the late 90s, when that first discovery of a protocluster was found, we've discovered about 60 to 70. Which is small, as we've discovered thousands of clusters. And if these are the ancestors to the clusters today, we still have a lot of work to do. And we still have this issue of the protocluster zoo. So in the last bit of this talk, I want to talk about the frontier of protocluster research, some of the recent advancements, and the future outlook. So the James Webb Space Telescope has been revolutionary for this field. It's allowed us to peer deeper into time and detect the earliest stages of cluster formation. This is the image that I showed at the top of the slide. This is actually a relatively nearby galaxy cluster known as Pandora's cluster. And these things here are all kind of merging together. But hiding in the background, researchers have discovered that there's this distant concentration of galaxies shown here. If we zoom in a little bit, you can see them. Let's pop them out. These are 7 galaxies that are all at the same distance, clustered together in the early universe, 650 million years after the Big Bang. Kind of just to highlight how James Webb has changed in this picture, this plot shows the age of the universe on the top. And these are all the handful, not the entire sample, of clusters that we've found and confirmed in yellow. And in the blue background are the protoclusters that we've found. And if you add in James Webb, we're kind of filling in this really towards the early universe. So James Webb is really revolutionizing the way that we study protoclusters. The only issue is that it doesn't have a huge field of view, so we're really limited to looking at kind of only bits and pieces of what we think the protocluster is. Another really, really exciting discovery is this cosmic vine discovered by JWST. Is this chain of 20 ancient galaxies spanning 13 million light years in size. And this seen when the universe was 1.5 billion years old. So I talked earlier about these giant elliptical galaxies. How did they form? Well, we're actually starting to see evidence of this in real time. These are 2 galaxies that are starting to merge early on in the universe. Signs, potentially, of these giant ellipticals forming. So we're starting to answer these questions today. Some of the other recent advancements has been made with the ALMA Observatory. This is the Atacama Large Millimeter and Submillimeter Array. This is located in Chile, and it's sensitive to these longer wavelengths. And researchers have used this telescope to look at the earliest signs of the intercluster medium. So we're getting close to understanding how this thing formed and when this hot gas formed. So how they did this is they took advantage of this radiation from the early universe, the afterglow of the Big Bang we call the cosmic microwave background. And if we assume that this plasma exists, it should have some electrons that are moving around. And as you can see in this animation, these red lights from the cosmic microwave background interacts with the electrons, changing from red to blue. They're going from longer wavelengths to shorter wavelengths due to the scattering. And by measuring kind of this scattering, we can see the intracluster meteor forming. This is in the spiderweb protocluster 10 billion light years away. Other really cool recent advancements. So, as mentioned at the top of this, I study galaxy formation and evolution both observationally and theoretically using simulations. The next generations of cosmological simulations is helping us bridge theory and observation. So this is a visualization from the TNG cluster simulation. We're taking all the physics that we think is operating in the universe. We're evolving these systems from the early universe to today and seeing how they turn out and comparing that to what we observed. One of my recent papers, we looked at the size evolution of protoclusters, what's expected from these simulations versus what we observe. So just to go over this, these solid lines are kind of the full extent of what we think the protocluster should be. These different colors just represent how massive the cluster will be today once it's finished evolving. And if we overplot kind of the sizes that we use to find clusters, we find that we're underestimating their sizes. So this has huge impacts on how we infer their total mass today and how we even determine if these high distant densities of galaxies will even become clusters. Now on the observational side, I'm part of a team known as the C3VO team. It's a survey taking data from the Keck telescopes in Hawaii to try to solve this protocluster zoo problem. I mentioned earlier there's all these different tracers that we use to find protoclusters, star-forming galaxies, highly luminous galaxies, ultramassive galaxies. So what we do here is that we're trying to actually fill in this problem by getting distance measurements for all these galaxies. So this is an example of one of the protoclusters that we found in 2D, and then we also get these 3D representations. And we can start to answer and ask questions. So one thing that we found is that in the densest regions of protoclusters, we find more of these active galactic nuclei, these AGN, supermassive black holes that I mentioned before. So this can tell us about how these processes change the galaxies inside them, potentially helping give rise to these elliptical galaxies that we see in clusters today. And lastly, we looked at the fraction of star formation that has happened in clusters as a function of time. So let me walk you through this plot. So on the y-axis, we were seeing more star formation as we go up. X-axis, we're seeing going further back in time. Now, these lines show the theoretical predictions of how this should evolve. But now we're actually starting putting data onto this plot. So the star here represents a result from one of the protocluster study and in our survey. And we're finding that our measurements are consistent with the theoretical predictions of extreme star formation happening in galaxy protoclusters. And this happens near a point that's really important in the age of the universe. It's known as the epoch of reionization. So if we look at kind of this evolution of the universe, reionization happens here. This is the last change, major phase change in the universe, when hydrogen went from being mostly neutral to ionized. And we really want to understand how that happened and what are the sources that drove this change. So we think protoclusters are potentially the drivers of this. And it's just as a visual to show. Kind of all this red is the neutral hydrogen, and these are the sources in the simulations that would drive it. So we're really making a lot of progress. There's still a lot of questions to answer. But it's a really exciting time to be in the field of galaxy protocluster research. So returning back to this plot that I showed earlier, the cumulative number of discoveries of protoclusters as a function of time, starting from the late 90s to today. So over time, again, we found around 60 to 7 that we've confirmed. We gathered distance measurements, we got rid of those interlopers, those imposters that we mentioned before. But in a year and a half, NASA's big thing will go into space. It's the Roman Space Telescope. What's so special about this telescope? Compared to Hubble, its field of view is 100 times larger, while maintaining the same resolution. Meaning that we will be able to scan the sky and find all the wonderful flare clusters that will excite me and boost my research. So we'll go from less than 100 to some predictions finding over 1,000 protoclusters discovered with Roman over the next decade. Really peering into the earliest stage of galaxy cluster formation. But I'm also interested in looking at the synergy between Roman and other telescopes. So I talked about Rubin earlier, largest digital camera humans ever produced. We can see things that are very faint. There's Euclid, it's another wide area telescope in space. And of course we have JWST, that has this sensitivity to the near infrared wavelengths. We can peer really deep into the early universe. So combining all these together, I think that the future of a protocluster is extremely bright, and I'm really excited to be a part of that. So to end this off, I would like to share a quote. So we talked about these extreme distances, deep time, and this quote always grounds me, kind of brings me back to Earth. It goes, "She had studied the universe all her life, but had overlooked its clearest message. For creatures such as us, the vastness is bearable only through love." Now, we occupy a very small time and space in the universe, and it can be daunting when we're confronted with that. But the connections and the time that we spend with the people that we love makes it worth all the while. So with that, I want to thank you all for sharing your time with me tonight.
Does anyone have any questions? Yeah.
To understand the early universe and the concentrations and the stuff that was happening, isn't that legacies coming from before the Big Bang? We have to understand what the Big Bang was. Was it, say, a black hole in a previous universe or something like that? And the remnants of that, like in this universe, when a supermassive black hole swallows another black hole, what are the that would, to me, would seem one of the few things that may have an effect on the other side of the singularity. There are two singularities. I imagine all other matter in space or time, whatever, doesn't make it through a black hole. Yeah.
Right, so observationally, we're kind of limited to like how far back we can go, and we can come up with theories of kind of what happened before the Big Bang. We really don't know. That's the answer. In terms of what I'm interested in is, if you look at the cosmic microwave background, this first afterglow of the Big Bang, it's kind of how far we can go back. There's all these subtle differences in densities in the early universe. It was small and compact. And these things, as the universe expanded and grew, these densities started to expand as well. And this is what we think are the seeds of clusters today. So that's kind of how far back my science can go. Before the Big Bang is something that...
But would that tell you, I mean, if you modeled what, say, a black hole does going through another black hole, like a supermassive one, wouldn't the result of that, if it manifests, if you get stuff in this universe that could be the result of that, wouldn't that, say, verify the fact that this universe might just be a black hole in another universe or something?
Theoretically, people could study that. That's kind of beyond the scope of my research. It's fascinating to contemplate where our universe came from and this initial singularity. One theory that I kind of like is this multiple universe theories, where we happen to live in the universe, but things went right, and we're here to ask those questions tonight. Otherwise, we wouldn't be here. But thank you for the question. Yes?
So why are galaxies clustering in these like dense pockets or whatever?
Yeah, great question. So that kind of goes back to like the early universe, where there's regions of high density and low density, but at early times they're kind of subtle, but they grew kind of exponentially. That all the matter started to clump together in one region, and there was less matter in other regions. And clusters, we think, are the final product of all of that. So all of it's due to gravity and some initial conditions where things were more dense in some places and less dense in others.
And over time it becomes less dense. Like the more recent galaxy clusters are less dense.
They're denser in their core region. Back in time, they were more extended. So you have all these matter that kind of is destined to collapse together to find the clusters we see today.
My definitional question about galaxy clusters. So we see a bunch of galaxies and you draw a circle and you say this is a cluster. Like how do you define the boundaries of that? Like,
That's an excellent question, and it's a question that a lot of people have thought about. So yes, we look into the space and we see these overdensity galaxies, making sure that we get good distance measurements. Another way is to use these signposts to make sure that there's hot gas there that we can see in X-rays, for example. So, okay, that's a cluster, but how do you draw a boundary for what's a cluster or not? So we can define a boundary of things that are gravitationally bound. We can draw a boundary where the cluster is actually collapsing versus kind of being pulled away from the expansion of the universe. So we draw a lot of circles around clusters, and I usually stick to the region where things are gravitationally bound. But the entire structure is interesting because things could kind of fall into that region too, become bound later in time. There was a question here first.
So this is kind of dated, but I thought elliptical galaxies kind of evolved when you're saying they might have just born elliptical from the beginning,
No, so yeah, elliptical galaxies are thought to, like you mentioned, form from spiral galaxies, right? So you have these spiral galaxies and they can have some gas stripped away, some mergers, and create these ellipticals, right? But we're seeing these elliptical galaxies earlier than kind of we previously thought. I showed the cosmic vine where you have like these two elliptical galaxies already been formed 1.5 billion years after the Big Bang. It's kind of understanding how did those things form is still a question by studying protoclusters can help us solve. Question in the back. Yes.
Are you finding any evidence that the physics in the early universe is different than the physics we see today?
So I talked about supernova hope. And there's measurements of the expansion rate in the early universe that are lower than what we measure today. So it seems like the physics, maybe some people think that the physics is changing. That's still an active area of research, understanding how these things evolve with time. But in my research, no, I'm not actually probing kind of the cosmological aspect of the universe. Question here.
You mentioned a gravitational lens. What exactly are you capturing when you say that?
Yeah, so I showed the animation of kind of you have the space-time, think of it as flat space-time, then you have like some matter here, and it kind of curves it. And it's the matter, the presence of the matter itself, that is the lens. So it bends space-time, light from the background actually interacts with it. Instead of going straight, it kind of curves. And the cluster itself is the lens. So it can magnify light, allowing us to see things more distant than we could see otherwise, because they'd be too faint. You can get multiple images. In the case of the supernova, where you can see a supernova that arrives at different times and put some constraints on the distance expansion rate of the universe. So it's a cluster itself.
So if I'm understanding right, you're still capturing light, but you're just performing calculations on how much it's spending essentially magnifying.
Yeah, so when it comes to looking for this, you actually have to model the lens system. So you, like in your models, you got to say, okay, how is matter distributed in order to give rise to what we observe, right? So you have a model and you compare it to observations. You kind of like want to tweak the model until you can match what you see, and then you can say, okay, this is like the lens is how mass is observed, and is how much mass we think is there. We'll get one question and go.
Sorry for the basic question. I hard time grasping the timeline. When you said on the in the cluster, when the galaxies ran into each other, how long did that take?
Oh man, I don't have that number off the top of my head. I apologies.
Is it like 10,000 years? Is it a million years?
Yeah, I'm going to say on the order of hundreds of million. Yeah. That would be my, yeah. Good question though. And then we had a question.
Does space-time actually flow into a black hole?
I think that's beyond the scope of my research. I don't necessarily study black holes, but you would imagine so, right? So you have black holes, there's ways to form them. You have these massive stars. They die, collapse, become super dense, and you create a region where no light can escape. So space-time itself is intrinsically made of the black hole, from my understanding.
And so it could be flowing into the black hole.
Right, right. I mean, I guess like there's the idea of these wormholes, right, where you have like two pieces of space-time. You have some entrance and exit. I don't recommend jumping into a black hole, though, but yeah.
Maybe last question, but we'll be here to answer more afterwards. So yeah.
Yes.
Do elliptical galaxies have supermassive black holes?
That's a great question. Yes, they do, actually. So anyone remember the kind of image of a black hole that we saw a couple years ago? Yeah, so that was actually one of the massive elliptical galaxies in the Virgo cluster. M87 is the name of it. So they do have black holes, and sometimes they're shooting out jets of radiation that we can also see. And that might be one way that the elliptical galaxies kind of lose some of their gas and become these red and dead galaxies. Because the gas is the fuel that we need to make stars.
Please join me in thanking Dr. Baxter.